All right, Professor, what have we got today?
Messier 72. It's a globular cluster. Here's a picture of it.
It's not a bad one.
It's nice. Some of the globular clusters are very centrally concentrated. This isn't one of those. It's kind of more of a loose scattering of stars. It's a very long way away. It's about 50,000 light years away, so it's kind of on the other side of the galaxy. What I was thinking about is, well, what can you do with a globular cluster? You can take a picture of it, right? And then what can you do next? Well, you could actually take another picture of it. You'd expect the two pictures to be more or less identical. But actually, it turns out that's not quite the case, because there are always a few stars in any cluster that are actually variable. And so you'll see a few stars have got brighter or fainter between the two images. And if you take a whole series of images, obviously you can then track to see if is it just fading away, is it getting brighter, or as is almost always the case, is it kind of periodically changing over time, getting brighter and fainter again. So that's exactly what these guys did. So you see the time series photometry of the globular cluster NGC 6981, which is the other name of Messier 72, variable star census and physical parameter estimates. One of the trickier things with globular clusters when you're trying to pick out the properties of individual stars is actually they're quite crowded. So you end up, with this sort of confusion effect that you can't see if you're seeing one star or several stars superimposed or overlapping with each other. So the neat technique they use in this particular analysis is a thing called difference imaging, which essentially just means you take one image, you take another one, and you subtract one from the other. And of course, if nothing had changed, then there'd be nothing left in the difference image. But what you get is that if a star's got brighter, then it'll suddenly pop up, and if it's got fainter, then it'll appear as a kind of a negative star in the image. And so from that, you can actually pick out the variable stars. So this plot up here is one of these color magnitude diagrams. So basically it's how bright are the individual stars, and this is now the average brightness of them, because of course these ones are varying a bit. And how blue is it that way, with blue things over here, red things over there, faint things at the bottom, bright things at the top. So there are this thing called the main sequence down here, which is the ones that are turning hydrogen into helium. There's this thing called the horizontal branch here, which is where stars are turning helium into carbon. Basically, what you're seeing are stars of slightly different masses that are at different stages of the stellar evolution. And then the ones that are in color here are the ones that they've identified as variable. So what's really going on in these stars is there's something making it unstable, making it pulsate. And the something in this case is a weird instability. Basically, the star's made mostly of hydrogen and helium. Sometimes, in the later stages, the helium turns into heavier elements. But primordially, when it started out, it was just the hydrogen and helium and a little bit of heavy elements that were there in the universe. So helium is 2 protons, usually 2 neutrons and 2 electrons. So you've got the nucleus and then the 2 electrons kind of orbiting around it. When you heat helium up, you rip one of those electrons off typically, and then it becomes singly ionized helium. And then if you heat it up some more, you rip the second electron off and it becomes doubly ionized helium. And so as you go down into the star, it gets hotter and hotter and hotter. You reach the point where the first electrons are getting ripped off the helium, so it's singly ionized helium. Now, if you imagine taking that bit of the star and just randomly, it just gets compressed a little bit. When you compress it, it's going to heat up some more. That act of heating up some more will make that singly ionized helium turn into doubly ionized helium. So it's got hotter, it loses its second electron. So now we've just basically got 2 protons and 2 neutrons and no electrons left around it. What we've done now is we've compressed it a little bit. We've created this doubly ionized helium. Suddenly we've created this layer which is much more opaque. And that's essentially like putting a blanket on the thing. It sort of holds the heat in because the light can't get out anymore. So that then causes the interior of the star immediately within that sort of shell, to get hotter because the radiation's getting trapped. It heats up. That act of heating up then makes the thing expand again. The expansion makes it cool down. And when it cools down, that doubly ionized helium turns back into singly ionized helium again. It recaptures its electrons. And we're back where we started. So it re-expands to where it was and then keeps going. And now it's a bit too far, so then it collapses back down again, and the whole thing just repeats itself. So it's this weird cycle that's essentially being driven just by the fact that the helium keeps changing between being singly ionized helium and doubly ionized helium, that kind of drives this weird cycle within the star.
Now, only a very few stars are doing this, though. It's not like they're all pulsing like this.
They're not. And that's the interesting thing. So what you want for this effect to work is you need to have this region which is just at this magic temperature, sort of Goldilocks kind of temperature, not too hot, not too cold, to be just on that hairy edge of things becoming doubly ionized. Right? I mean, if the star's hot enough, then that region's going to be right near the surface of the star, so there isn't enough of the weight of the star to push down on it. If it's too cool a star, then it's very cool on the outside. As you go downwards, you'll eventually reach the point where it's hot enough for this effect to happen. But that's now so deep in the guts of the star that all that weight of the star pushing down on it stops the process. So you need it to be at just kind of the right depth in the star. So remember, this axis here is a measure of colour, but it's also a measure of temperature, in that redder things are cooler and bluer things are hotter. And it's only these things in the middle that have this magic property. And in fact, if you go up through the colour magnitude diagram, there's this thing called the instability strip that kind of runs all the way up here. any star that lies in this region is likely to show this instability. So, for example, I think we talked about Cepheid variables in the past. They're driven by exactly the same process, but they're very massive stars, so they're way up here somewhere. The ones that were picked up here on this thing called the horizontal branch, so these ones that are turning helium into carbon, they're called RI Lyrae stars. And then the two little ones that are down here are called Essex Phoenicis stars. These are also variable stars, driven by the same process. But the weird thing about them is that most of the main sequence stars up here have disappeared because they were more massive stars that already died. So the only ones that are left should be down here. But these are actually up here. So they're main sequence stars, they're lying on the main sequence, but they're actually more massive than should be in this cluster, because anything this mass should already have disappeared. Again, this is something we talked about before. These are things called blue straggler stars. So these are actually illustrating two phenomena at once. They're illustrating this instability strip, but they're also blue stragglers because they lie kind of beyond the end of the main sequence. So they're that weird type of Essex Phoenicis variable star.
Professor, would living on a planet going around one of these stars be interesting or catastrophic?
So in this particular case, you'd be hard-pressed, I think, because there's been a lot of discussion about whether you could have life in globular clusters. And it's not terribly conducive to it, partly because the stars are very close together, and so there's a good chance that another star will come whizzing past and mess up your solar system. But also they're very low in these heavy element abundances. And so whether there's enough heavy elements there to actually form rocky planets and people, I suspect probably not. So these little ones down here, the Essex Phoenicis ones, the period of pulsation is about an hour. Okay, so it's actually varying on an hour's timescale, so they're quite rapid variations. So you would have this weird thing that your star would kind of visibly get brighter and fainter during the day, because I guess we're used to that because it gets cloudy from time to time. So it would really be that kind of effect, that it would just, sometimes it'd be a bit brighter, sometimes a bit fainter.
But it wouldn't, so it wouldn't there'd be a civilization destroying event every 24 hours.
No. But I suspect probably you'd end up with some quite strange myths coming up. Right? You'd have some mythical reason as to why your star was doing these things. The myth would come first, the physics would come later.
Talking about what's inside them, but it just encapsulates for me just how unique this catalogue is.
Nice and gentle.
Okay. It's all right. It's not too heavy.
Okay, Brady, would you like to take her feet?
Take the feet?
Yep.
Okay.